Alright, this little mini lessons over wind, which is what chapter 8 in the book is about. So wind is horizontal movement of air. These are horizontal movements that are caused by the differences in air pressure. The differences in air pressure are caused by the differential heating of the Earth's surface. So wind is created by the fact that the sun heats the surface differently, because land will heat up differently than water will. That will create areas of high pressure and low pressure, and those differences will end up creating the wind. So that's kind of what wind is all about. Pressure gradient force is where the Earth likes to fix an imbalance. So that whole taking the sun, heating the Earth differently, the land versus the water. If you heat the land, then you're going to end up having the air rise. If the air rise, there will be less air molecules at that area, so that would be considered a low pressure because there's less air molecules. And then it's an imbalance and the Earth has to fix it. So the pressure gradient force is talking about the fact that the Earth is trying to fix those areas that have less air or lower pressure because of that less air molecules, taking it from an area that has more air molecules. So from a high pressure to a low pressure. So the pressure gradient force is movement of air molecules from high pressure to air molecules in an area of low pressure. So areas of surplus to areas of deficit. Now, when you're looking at the pressure gradient force, the closer those highs and lows are together, the faster the winds are going to be. So the more tightly packed the isobars are, those lines of constant pressure, then the stronger the wind. The further apart the isobars or even the two pressure systems, the less wind is going to be in between. So the pressure gradient force is greater the closer the high pressure and the low pressure are to each other, like in relation on on the surface. So that's one property of wind. Another property of wind is called the centripetal force. That's what they call the center-seeking force. There's the Coriolis force, and that's created by the Earth's rotation. In the northern hemisphere, winds are deflected to the right, in the southern hemisphere, they're deflected to the left. Now, the Coriolis force only works on the direction of wind, not the speed of the wind. So it has nothing to do with the speed, it only affects the direction. The stronger the wind is, the greater the deflection is going to be. So it's going to be the strongest at the poles and pretty much zero at the equator, which is why you don't get hurricanes to form exactly on the equator, because there's no Coriolis effect to give them that spin. Now they can form somewhere else across the equator, which still doesn't happen all that often, but it can. But it can't form right on the equator because it doesn't have that Coriolis to give it its spin. When you're looking at the two, the stronger the wind, the more that deflection is going to take place. So the faster the wind, the more the deflection. Again, the Coriolis doesn't affect the speed, it just affects the direction of the actual wind. When you have those forces, the Coriolis force and the pressure gradient force in balance, then you have what's called the geostrophic wind. And the geostrophic wind would be like your jet stream level winds. So whenever you have those two pressures, or two forces, balance, then it creates this wind that goes parallel to the isobars, the winds that are high above the Earth's surface, the geostrophic winds. Geostrophic wind is a very straight wind, and it's a very fast wind because there's no friction involved with it. So straight and a fast wind. So friction is another force that I just was talking about, and then there's gravitational forces, and those only affect the parcels that are rising and the parcels that are sinking. Now friction slows the winds down, but it only does it at the surface, because friction with the land or friction with, in our case, buildings and trees and that kind of stuff will slow the wind down. So there's no friction aloft, so winds above the Earth's surface are going to be faster than winds at the surface. Now when you get all five of those forces that were just listed, these are the things that they cause. You get what's called hydrostatic equilibrium, where you're not having any rising or sinking, so things are in balance. You have the pressure gradient force and the Coriolis force in balance, and you get an upper air wind called that geostrophic wind, and what's called a gradient wind. But the only difference between the two is that the gradient wind is a curved wind. So it would be like going around highs or lows, or going around the bend in like the ridge or the trough. Pressure gradient, force, Coriolis effect, and friction will cause your surface winds. So basically the friction will have these two forces not in balance anymore, because friction will slow the wind down, and Coriolis effect doesn't affect winds as much the slower they are. You get surface and upper air pressure systems from all those 5 forces interacting. This is the hydrostatic equilibrium, where you've got pressure gradient, force, and gravity, and basically it's an acceleration of 0. This is permanent. This is always going to be in place, because you're always going to have the higher pressure at the surface, the lower pressure above, so high to low, so that pressure gradient, force going up, and gravity is always going down, so those two are always going to end up being imbalanced. But you'll get some slight changes in that balance of one being slightly more stronger than the other, which can give you changes in your speed vertically. We're not going to get into too much detail over that, but there's that geostrophic wind where you had the pressure gradient force and the Coriolis force in balance. So it makes that straight wind. It's a horizontal, it's frictionless because it's above the Earth's surface. We talked about how surface or winds that are above the surface blow parallel to the isobars. So you're looking at a starting point. Force is not quite in balance, it's pressure gradient, it's Coriolis. And then once they're in balance, and that wind is parallel, you see here's the isobars, parallel to the isobars. Now, gradient wind is still frictionless, it's horizontal. The difference is that it's curved, and that's because your pressure gradient force and Coriolis aren't quite in balance. One is stronger than the other, and you will get the resulting centripetal force, which means it'll give it a curve, it'll actually let it turn. That Coriolis force will be the one that's a little more dominant, which will allow it to deflect one way, the right or left, depending on which hemisphere you're in. And you'll get it to be able to curve, which will be curving around high pressures or around low pressures. And remember, surface winds, friction's involved, so it slows it down, and then that's when the actual wind will cross the isobars. So that's why you see on the surface maps the winds crossing the isobars, but on that 500 or any of the other ones, 500 or 300, you'll see that that actual wind will blow parallel to the isobars because friction isn't involved. Okay, so looking at it in terms of the 300 millibar jet stream level, it will end up having troughs, which are the dips like the U's, and it'll also have ridges, so it'll be upside down U. Notice that winds coming out of a trough are faster, the winds going into a trough. These are all blowing parallel to the isobars. This would be the geostrophic wind, where it's straight, where it takes this curve, and in the trough, that would be considered a gradient wind. Alright, so some continuity of the wind. Now, what does all this differential heating mean, and how does it all set up? Because we're going to look at a kind of cross-section of the atmosphere, what actually is going on with the wind. Alright, here's my lovely example. There's the sun, so it's daytime. There's water, and there's land. Okay, when we're looking at this, we know that the sun will heat the earth differently because the land's going to heat up faster into a higher temperature, which is going to force the air to rise. So you're going to create a lower pressure on the land because you've taken these air molecules and moved them up, and eventually you're going to hit the top where it has to diverge, and it would go both directions, but I'm just going to focus on this end. Now over here it hasn't heated up as much because of the fact that it's water and it takes a lot longer. So So eventually that air is going to have to descend. So this area over here has this higher pressure. It's got more air molecules because it's not heating it up the same, so that way the air will rise as it did over land. So you have your pressure gradient force. So you're taking these extra air molecules over the water because it hasn't heated up as fast, moved them over land to where there's less air molecules. That's pressure gradient force. PGF. It's taken over. And you have this setup. This is called a sea breeze. So you see this sea breeze going on. You're going to get that, usually by the time all that heating up the land, it's usually like late afternoon. And you'll get a nice sea breeze. So, and it's really isolated. If you've ever been to a beach line, you only really feel it really close to the water. After that, then you don't notice the effects quite as much. Okay, so here's my opposite going on. There's the moon. It's nighttime. We don't have heating going on, so we're going to have some kind of stuff going a little backwards. So now it's taken all this time, and finally this has heated up enough, but also the land has cooled because it's gotten nighttime, so remember it cools off faster into a lower temperature. So now you kind of have this backwards pattern going on where you're going to have the air rising over here, and you're going to have the air sinking over the land. So you have higher molecules of air pressure over land, and now it's lower because it took a long time for this to heat up, and now it's finally releasing. So now you have this effect going on. And again, it goes both directions, but we're going to look at it just in terms of right across the land. So you have your low pressure now over here, and high pressure is now, so again, your pressure gradient force, high to low. Air rising for the low pressure, air sinking for the high pressure. And now you have what's called a land breeze. So your land breeze is a much warmer breeze as opposed to the sea breeze being a lot cooler, bringing that cooler air over the water. So this is the land breeze, which again usually happens at overnight, and then because it takes a long time for once the sun's up for everything really to get going, then the land breeze can last all the way up through the noon hour depending on circumstances. If you've ever been to a beach line and you notice that, especially on the East Coast, where you're in the summertime and you have that land breeze still going on in the morning, and you have those biting flies because the the breeze is still going out towards the water, so you get all these flies and stuff like that. But once you get towards the afternoon, by the time that switch happens, where the land is finally heated up a lot more, and then the low pressure is now located over land, and you get that sea breeze coming in, and it's much nicer. And you get that nice breeze in, and then those little biting flies aren't there either. So that's your difference between your land breeze and your sea breeze. So let's take a quick look at high pressure versus low pressure. We already know that high pressures are, this is all northern hemisphere, clockwise and out. So it's called divergence. So you've got air sinking, hitting the ground, diverging, spreading out. Low pressures, winds blow counterclockwise and they go inward. And that's where you get convergence, so the winds are coming together at the surface and making the air. Look at it like this, where you have your high pressure and your low pressure. That friction will allow those winds to start to either move in towards the low or out away from the low. So you'll start to see that high pressure gradient force really strong as you get down towards the surface, because you have those differences of the friction taking place. One other way to look at it, kind of cross section, and it's the same idea as looking at the sea breeze versus the land breeze that we just did. And you can see at a low pressure, the air is rising, and at a high pressure, the air is sinking. You've got this high to low going on. You have divergence aloft. And you're going to move all that over to the next area, which is the one that has the divergence. And at the surface, so you can get that moving the air molecules up, higher pressure to the less air molecules because more of them moving down, so you get that upper level high versus low pressure gradient force as well. So it works in both the surface and the upper levels at all. This is the cross section of what the highs and lows look like.